Let's now see an alternate version of radix sort known as most significant digit radix sort. So here's a bunch of words that you may have possibly learned. They're particularly famous long English words. I think anti-disestablishmentarianism is probably the most famous among them. And I'm using this as an example to show why LSD sort is not so good. So think about LSD sort trying to sort these words. Well, it doesn't compare anything. It looks at M, N, M, S, S. Okay, it does some stuff. Then it does S, O, S, U, I, and so forth, working its way right to left. However, you and I looking at these, we immediately see that anti-disestablishmentarianism should be the first word because it starts with A, which is earlier than the others. So MSD sort will be relying on that same idea to avoid doing too much work of working from the most significant digit to the least. So let's just see if it works. Let's say we do MSD sort just like we did with LSD sort, working from left to right in this case. So we sort by all the A, B, C's, and we sort by the top digit, giving us the A's, the B's, the C, and the F's. If we repeat this process 2 more times, once for the middle digit and once for the rightmost digit, will we arrive at the correct result? I'll let you think about it. Okay, I'll give you a hint, a big hint. It's no. Why? Give me an example that shows that it will not arrive at the correct result. Okay, so the answer, or the one that jumps out to me, I mean not immediately, but after looking at it for a while, is, for example, if we look at bad versus add. So here, the most significant digit sorting does make sure, when we counting sort on the most significant digit, it does make sure that add is before bad. But then, when we do a counting sort on the middle digit, bad ends up at the top somewhere, and add ends up down here. So this is extremely bad that bad should end up above add. That's wrong. And if we then sort by the rightmost digit, because they both end in D, that's not going to help us at all. Bad's going to stay above add when we do our next pass of counting sort. So how do we fix that? Try and think about that. So LSD sort done in reverse doesn't work. So you need to figure out a way to fix it. And so my hint is to note that here are my A's, here are my B's, here's C, and here are my F's. Make it work. All right, so the key realization is to recognize that we want to treat each of these as separate subproblems. When we do our counting sort, we shouldn't include all of the keys. We should include only those keys that have the same top digit. So for example, once we have sorted into, this is the exact same result here. Once we've sorted into this set of values, then what we want to do is sort only these top 2 using counting sort on the middle digit. So if we do that, we end up with 2 subproblems. One that is of size 1, that's ace, and the other of size 1, which is add. Now at this point, because we have 2 subproblems that are size 1, there's nothing else to do. Okay, so next we consider bad, B, bad. Okay, so here we go, bad, B, bad. Now here we observe that this top subproblem is size 1, so there's nothing else to do, but bad and B, there's still 2 keys in the space, so to speak, or the set of things we're considering. So now we need to do a counting sort on the middle digit, and, we've already done on the middle digit. Now we need to do a counting sort on the last digit, which would give us bad and B as separate subproblems. Okay? If they were still equal, that would be fine, because we would have looked at all of the characters and we're done. All right, so now we have another subproblem, which is cab. This one's already size 1, so we don't do anything. And if you're wondering how this actually results in sorting, you can imagine that over here separately, I have an array, and I will copy ace, add, bed, B, and cab into it in that order, and they're all there, done, and waiting for the last 3 keys to be filled in. So to do that, we have fad, fee, and fed. We're going to do a counting sort on the middle digit, so we end up with fad, fee, fed. There are still 2 keys left in this subproblem. We can think of this as the FE subproblem. And this, in turn, is going to give us 2 subproblems when we sort on the rightmost digit. We have fed and fee. They're both of size 1, and we're done. So we copy over fad, fed, and fee, and everything is now in sorted order. And it works perfectly. It works and we saved ourselves a little bit of effort. As you note, we never even looked at this A or this B. We never looked at this E or this D, and that's work saved. If we'd done LSD sort, we would have had to look at every single character, whereas here we only looked at some of the digits. Okay. So question for you. What is the best case for MSD sort, and what is the worst case? And I'd like you to give your answer in terms of N, W, and R, where N is the number of items, R is the alphabet size, and W is the width of the widest key. Okay, just wait. All right, in the very best case, we finish in one counting sort pass. That is, we only look at the top digit, and it just so happens that all the top digits are unique, and therefore the total runtime is just N plus R. In the worst case, that's when we have to look at every character. So that's where we have, for example, all of the keys equal, or all the keys almost exactly the same. They're really long, let's say. So in the worst case, we have to look at every character, or almost every character, and so it degenerates into LSD sort. We go on the top digit, the next digit, the next digit, the next digit, the next digit for all of them, and we end up with a runtime that's WN plus WR. So it lives basically between the runtime of counting sort and LSD sort, just depending on how bad the input is. All right, so to summarize, MSD sort has a runtime between N plus R and WN plus WR. Now, for reasons that are a little beyond the scope of the class, it also has bad caching performance. That is, it tends to look at really far apart items in an array, and if you're curious about that, you will learn about it in 61C, but it's beyond the scope of our class. In terms of memory usage, I didn't show this, but its runtime is N plus WR. Now, if you're curious why this expression, you can either work it out yourself. It's a challenging but not crazy asymptotics problem. And if you're curious about the runtime in, say, the average or the expected case, I urge you to look at the optional textbook, though I will note that even the optional textbook doesn't really go into much detail because it's a bit annoying in terms of theoretical analysis. The bottom line, though, is that MSD sort should be somewhere between counting sort and LSD sort. Just depends on how bad your input is. So what's important here? Well, what's important in today's lecture is that we have seen a new, totally different approach to sorting that relies on counting, that actually generalizes to strings of alphabetical keys only. Now, in terms of which one's better, like should we be using these comparison-based sorts or these radix-based sorts, I'm going to leave that for next lecture when we'll talk about this, but the answer, it turns out, is it's kind of complicated. All right, so to round out today, I want to remind you that there's this very nice set of videos that are the sounds of sorting algorithms, and there's actually some problems you can ask yourself as you watch them that I'm not going to read out loud, but you might find it interesting to try out. So let's look at LSD sort real quick. Okay, so here is LSD sort. There we go. This is LSD sort happening. So if you've understood this lecture, immediately you can rewatch this video and understand what's going on. What are the steps that are occurring? And you can even ask yourself, what is the size of the alphabet and how many digits are in the keys? And so my challenge to you, watch that video and figure out the answers to those two questions. And by the way, there's also MSD sort, which you might find interesting to watch as well. All right, that's it for today. So I will see you next time when we'll do a little more analysis comparing our old sorts to our radix sorts, and then harken back to the old days of data structures and give some compare and contrast between sorting and data structures.